So after having discussed about the inertia tensor, we will now go on to discuss equations of dynamics for a rigid body, and it will make extensive use of the inertia tensor which we have just learned about. So under this heading, the first thing we can go for is angular impulse moment of momentum relation. Okay. So we have already studied about the angular impulse moment of moment equation. So let's just first write what we had learned about this subject before. Uh, let's see if I can find that. Point 0.53. So we had yes, we had equation 2.53. This was from T1 to T2, T1 to T2, MA TT equal to HA at T1, HA at T2, DHA. This is equal to HA T2 minus HA T1. Okay. So the external angular impulse about A equals the change in the moment of momentum. That's what we had learned. This was equation 2.53. Okay. So this could have been any point essentially. Okay. Now we want to apply the same concept over here. If point A is equal to C, or C is the center of mass, or the acceleration of A in the inertial frame is equal to 0, or acceleration of A in the inertial frame is along AC, okay, for all t element of t1 comma t2. Then you can write that I angular of A t1 comma t2 is equal to delta HA. HA T2 minus HA okay. Now we want to, so A is definitely a point on the rigid body. In that case you can write HA from the previous discussion on the inertia as Ij a omega j ei. Okay, so this comes immediately from the previous discussion which we have just had. Okay, if a is a point on the rigid body, okay, if it is not a point on the rigid body, then it can be written in terms of the center of mass. So HA would be equal to HC. So I will directly write what HC is. It is Iij, because C is definitely a point about which this can be written. So in this, when we were writing this, there was a discussion of what can A be. Okay, so please go through that and check back and see why is it okay to write this expression for HC plus RCA into MVCA. Okay, this is if A is not its material point. So one of the requirements about this has been that the body must be rigid, must be rigid at t equal to t1 and t equal to t2, not necessarily in between. Okay, so this equation 3.19 is valid for the, so this is something which you should verify and be very clear. Why do we say this? So in between it is allowed to be deformable or rigid. Okay, so let's just write so if you have, say, the component of MA along an axis is 0, then this equation, okay, is only valid along that particular component. Okay, so for example, HA is a vector, it can have any directions. Okay, and if M is equal to HA over here, where did it go? Okay, something like this. If the component of MA along an axis fixed in the inertial frame is 0, then equation 3.19 implies that the component of HA along that axis is constant. Okay, so in that particular constant will be 0, that particular component will be 0 of HA, and obviously then this will be true along that particular axis only. So again, I mean, if you have, this is coming from equation 2.54. Please revise this. If you have not, please pause the video, go back, revise, and then come back. So for an instantaneous, okay, remember one of the times was taken as tending to T2 minus T1 was taken as tending to 0. For an instantaneous angular impulse acting on a rigid body at T1, if point A is such that A is either equal to the center of mass or the velocity of A in I frame at T1 plus is equal to velocity of A in the I frame at T1 minus. Essentially it means that the acceleration is 0 for this instantaneous case. Then I angular of A T1 delta HA equal to HA T1 plus. Okay, so this is a case where clearly T2 has been replaced by T1 plus and T1 by T1 minus. It's an instantaneous angular impulse. Okay, now let's draw a diagram perhaps, or we'll do that later. So if you have your x, y and z axis attached to the rigid body, and k remains, we have to let x, y, z axis attached and let k remains constant relative to the inertial frame. This implies that omega is equal to omega k hat. So in this particular case, I should write again, it's a material point of a rigid body which can either be such that A is either the same as center of mass, or the acceleration of A, the I frame is 0, or it's along the line AC. So we must write the component of this 319 along the K, along the K direction, because it is fixed over there. So I angle A Z, this shows that not a vector sign anymore because it's a component. T1 comma T2, T1 T2 M A Z T of dt, and same, now we have to write H A, so it should be IZZ A omega at T2 minus IZZ of A omega at T1. Okay, this is 3.21. Okay. So this is the equation which is valid rotation of a rigid body about a fixed axis. Remember, we have placed a condition over here that the body must, that the component of this which would be taken would be such that the MA along that axis is 0. Okay, so you have to now relate this to what we have just said over here. So let me write in red what happens to MA in this case. Okay, you have to relate it to 3.19 again. Okay, let's now take up a plane motion. Just first draw the center of mass. Okay, this has, say, a velocity vc, rotates by omega. This is c. Okay, this is the b. Okay, so let's call this as t. This vector is rcb. This vector. Okay, and clearly you have the x and y axis like this. So let's see. Consider the plane motion. You can also notice the sudden use of this I frame in these discussions. It is coming in because this angular impulse moment of momentum relation comes from the Euler's axiom, which is only valid for an inertial frame. So I hope you had noticed that. Now consider the plane motion of a rigid body wherein C moves in the xy plane and B is a point in the xy plane, clearly not on the body, fixed in I. Now that's clear from this diagram. Now look at RCB cross MVCB. Okay, this is equal to MVC D to K. Okay, so RCB cross VCB. Okay, so this is what we can say. Now T over here is the distance of B from velocity vector Vc through C. That is clearly shown in this. Now one of the things which is written over here is that it has a sign. So this is the signed distance. Okay. So the sign is really positive if cross product is positive. and it's negative if this cross product is negative. Okay, so that's how we are writing it in this form. Now the z component of the angular impulse moment of momentum relation for this point B, okay, this would be T1 of T2 and this will mean that you have T1 and T2 MB, the z component again, of T dt, that is equal to delta H B Z. Now how do you write HBZ? Well, you have to write it in terms of the center of mass. So omega plus MVC D in front T1 to T2. Okay. So H of B is written in terms of H of, so this is H of C. Okay, and just the Z component is written, that's why we are having this. Okay. Now the conservation relation corresponding, so this is equation 3.22. We have 3.21 and 3.22. So first obviously it will be in terms of B, 3.21 and 3.22. So let's first write 3.21. So this is about I angular impulse about A in the Z direction. Okay, now this quantity would be equal to 0 if this is the same as this. Okay, that's the conservation equation. So let me write that. If the angular impulse about point A in the Z direction T1 comma T2 is equal to 0, then Izz of A omega at T2 is Izz of A omega at T1. Okay, this is 3.23. Second is about 3.22. In this case, if this angular impulse about the point B, okay, point B is like this. Okay, it's lying in the xy plane for sure. Is 0, then it would mean that this entire quantity at T1 and T2 is the same. Okay, so let me do that. If my angular Bz of T1 comma T2 is equal to 0, then Izz of C omega plus MVC of T at T2 Izz C omega plus MVC of T at T1. This is 3.24. So these are the conservation relations which are corresponding to 3.21 and 3.22. I hope you are clear how we are able to derive this. So if you want to like write this in the instantaneous form, called the instantaneous variant, that's the word of the day. Yes. Okay, so I mean the restrictions on A apply. Okay, A is on a rigid body, and either A is equal to C or this of I T1 plus is equal to V T1 minus. Okay, so equation 3.21 in this case can be written as, graph A by Z T1 is equal to IZZ of A omega of T1 plus minus omega of T1 minus 3.25. And for B, okay, for B, what's the condition? That it must be, the acceleration of this must be same around this time, constant. Okay, so then this case 3.22 I angular of B Z into T1 is equal to IZZ of C omega T1 plus VC T1 plus minus VC T1 minus. Okay, so that's where we can sort of end our discussion on the angular impulse moment relation. We have written both the T1 and T2 and the instantaneous form of it. Let's now move on to write the moment of momentum equation. Equations. So apply, what we'll do is we'll just be applying the Euler's axiom in two ways. So let's see the two ways. To a rigid body, we are obviously referring to a rigid body, so I shouldn't be writing it. Euler's axioms. Okay. So what do they give? They give us F is equal to MACI and MC is equal to H dot C in I. This is 3.27. We have already seen, known and understood it. So let me just draw this. Okay, what I'll do is I'll draw a circle, not because I want this to be sort of a spherical body, but just because I want to bring home the point that it's the same body, and otherwise it's hard for me to replicate. So if you have the C as your center of mass, and say then you have this moment M1, you have the force F1, So this point is B, this is F3, this is F2. Okay, so you have, say, this as the external force system. Okay, see, then this would be you have the same point B. This is MC. This will clearly be equal to H dot CI, and you will have F. This will be equal to MACI. Okay, and then this vector would be called as RCP. Okay, so that's the first way of writing Euler's axiom, equation 3.27, as you see. We also know that the external force system, this one, okay, this is the external force system, this is the equivalent system at C. Okay, this can also be written as a kinetic system. So this external force system can be written as a kinetic system. So if you do not recall what a kinetic system is, please pause the video, go back and check, and then come back. Okay, so in this case we would have, say, C. There would be a, no, not this, there would be just an acceleration of C. There would be a HC dot I. Okay, we don't actually write these values, so I'm putting it in bracket because they are not written in the equivalent force system. And then you have B, so this is RCB. This is the equivalent kinetic system. Kinetic system. Kinetic system at C. Okay, so this has a force of force MAC of I and a couple of moment HC dot I. Okay, so we are putting this in quotes because we don't draw the force and the moments in the kinetic system, and similarly we have put this in brackets because we don't show this in the equivalent system at C. Okay. So if you want to write the moment of moment equation about any point B, okay, you can see the point B. You want to write this, obviously you will have to write it first about the point C. So MC is actually equal to HC dot I plus RCB cross MAC of I. This is 3.28. So this is clearly the moment of external forces. about B. So when you have plane motion, which is very common in many engineering applications, okay, in that case, say you will have one of the axis, say E3 is constant, and then we would be deriving these equations which you have just written over here, Euler's axioms, and this one 3.27 and 3.28 for some special cases. So let's try to treat those special cases, because most of the problems and applications of this only comes up in this case. Okay, so let's take up one motion of a rigid body with E3 is equal to constant, that is omega is equal to omega E3 hat. Okay, so this is how this rotation is happening about the E3 axis or the K axis, whatever is the system which one is using. Now in this case, let's write the uh, moment of momentum and omega relations which we had learned earlier in this chapter about the inertia tensor. So if A is a point of the rigid body or its 3D massless extension. So we had already discussed why this 3D massless extension is allowed. Okay, if you do not recall, please go and check. I mean, you have to see the contribution of this massless extension, and then it would be clear that it doesn't really matter that if it's a point on the rigid body or a point on the massless. Well, if it's not a massless extension, if it's just a normal extension, then perhaps we are not really sure. So I11 of A, I12 of A, I13 of A, I21 of A, I22 of A, I23 of A, I31 of A, I32 of A, I33 of A. Okay, and omega over here is 0, 0, omega. Okay, now this can just be simply written as I13A omega, I23A omega, I33 of A omega. HA is equal to, now I want to write this as a vector, so I should have, okay, anyways, 1 3 of A omega E1 hat plus I23 A omega E2 hat plus I33 A omega E3 hat. Okay, this is equation 3.29 for this special case. Okay, motion of a rigid body with E3 constant. So you can see that HA is not parallel to omega even in this plane motion case, okay, because if it was it would just have a component along the E3 direction, so it's not, okay. Now this is an important word. For convenience, we fix EI to the rigid body so that Ij dot A is equal to 0. Okay. So you should know just by looking at this where we are going, okay. See, this is equal, if you take a time derivative of this, then it is equal to MA, okay, and automatically if you take time derivative of this, you would require time derivatives of all of these terms. So that's where we are heading towards. I think you should get a clue. So if you fix your coordinate axis in such a way that this the change of inertia tensor about A, okay, is 0, okay. In addition, A coincides with C, or A is equal to 0, or A is along AC. You know why we are doing this, right? We have just discussed. Is along AC. Then you can write MA is equal to HA dot, and now in the I frame, H dot A EI hat, this is constant now, plus omega cross HA. Now this comes from where does this come from? Do you recall now? I think you should. Okay, so this was coming about when we were trying to write a vector in terms a time derivative. Okay, so let me try to look for that here. Hold on, let's see. Yes, so we had this equation 1.50. It was about writing the time derivative of any vector in the F frame in terms of the vector in the M frame with respect to omega of M with respect to F frame cross the vector itself. Okay, so over here the M frame is the rotating body, okay, and that's how we are able to write it. Okay, so this is what we had. Please go back and check and really understand, okay, just the equations itself will not be enough. You have to understand it well enough, otherwise it will sound very confusing every time we use this. Anyways, Now after this we just pick out HA from here. So that should be I13 omega dot E1 hat plus I23A omega dot E2 hat plus I33A omega dot E3 hat plus omega E3 hat cross HA will again I'll be writing this expression. So I13 A omega E1 hat plus I23 A omega E23 hat plus I33 A omega E3 hat. Okay, now obviously this E3 cross E3 would give you 0, everything else remains as it is. So I can write I13A omega dot minus I13A omega square E1 hat plus I23A omega dot minus I23A omega square plus hat. Okay, this implies, now see, this is actually all MA, right? MA. So the first component of MA, which is MA1, would be equal to I13A omega dot minus I13A omega square. Or I mean, you want to write this MAX as IXZA omega dot minus IYZ. This is 2, 3. This is, sorry, 1, 3. Yeah, omega 3 cross E1 would give you minus E2. Okay, fine. Okay, so IXZ minus IYZA omega square. The second component would be I23A omega dot minus I13A omega square MAY is equal to IYZA omega dot minus IXZA omega square. Then MA3 is equal to I33A omega dot, or MAZ is equal to IZZA omega dot. Okay, so A is again, I mean, it's either the same as center of mass, or the acceleration is 0, or the acceleration of A in the inertial frame is equal to is parallel to AC. Okay, there are few quick remarks which I can mention over here. Okay. Whatever you are seeing on your screen right now, this is equation 3.30. Okay. So say the vector, this MA is not actually parallel to E3. Okay, it has these two other components, and they are valid. This one, okay, or this one is valid even when E3 is not the principal axis. Okay, we never assumed that E3 was a principal axis, we just assumed that E3 was constant. Okay, so that's the first remark. It would have been visible with a star as well if we were using principal axis, but it's not. So you can use this expression irrespective of whether E3 is a principal axis or not. Okay, now look at equation 3.30. It depends on omega and omega square, omega dot and omega square. So it's a non-linear in omega. Okay. So that's something which you should be able to note. So the first way is not to be able to solve this. You first solve this one because it does not have omega square. Okay. Once you get what omega dot is, you substitute it over here and then you can get what omega square and omega is. Okay. So that's the way to proceed about this one. Then if you have this 3.30 applied to the center of mass, you can easily write them in this particular way. Okay. And you can remove the unknowns once you really know about the things from the center of mass perspective. So A is a generic point on the body, but knowing it from C, you can eliminate some of the unknowns once you have. So always begin with the center of mass. Okay, that's the whole point. So if your omega itself is constant, okay, meaning the omega vector, okay, this is omega, and if this is constant, then clearly omega dot will be equal to 0. Okay, and once that happens, a lot of these things become 0. So you should only have, say, MA. I'm looking at this equation. You should, omega dot is 0, so I should only have minus of I23 a omega square E1 hat plus I13 a omega square E2 hat. Okay, so this value is actually a constant. Okay, so a constant moment ma with respect to the body and a variable moment ma with respect to the inertial frame. So E1, E2, as you know, are actually fixed to the frame. Okay, we say that somewhere. We say that we can fix EI to the rigid body. So omega dot is as a vector itself is also 0. But since it's fixed to the body, this expression will be equal to constant. Okay, with respect to body, but this will be variable with respect to inertial frame because E1, E2 are actually rotating with the body. Okay, E1, E2 are not constant with respect to the inertial frame. Now in this particular case, if you have, say, E3 as the principal axis, then you know that if E3 is the principal axis, then we have learned before that I13 and I23 will be equal to 0. Okay, and this would automatically imply that this term is 0, this term is 0, so this would imply that MA is equal to 0. So this is important. It tells you that you do not require any moment ma to maintain a motion at a constant omega in the direction of a principal axis of inertia. So it's important, hence I should write it. No moment ma is needed to maintain motion at constant omega in the direction of principal axis of inertia. At A. Okay. So if E3 is the principal axis of inertia at the center of mass, then clearly the MC will be 0, just like MA is 0. Okay. The converse is not true. Okay, this will be discussed later. So this is in red and somewhat important for you to know. Again, I mean, if you have to write these equations 3.30 for an arbitrary point B, which is like not on the center of mass, then you can just write it in terms of the center of mass. So MB will be equal to MC plus RCB cross F, and then you can proceed. So normally you choose, when you try to solve problems, you choose this point B so that you have lots of unknowns over there, okay, because those unknown reactions will not contribute to the moment or the forces over there, okay. So that's why you can just do it about a point which has lots of unknowns, okay. So let me just put that. About arbitrary point B, okay. A was a point on the body or its massless extension. About B, life is not very difficult. You should have it about C. Plus RCB cross MAC of I cross MAC of I plus I x z of C omega dot minus I y z of C omega square. I y z C omega dot plus I x z C omega square j hat, and the last term is again I z z C omega dot k hat 3.31, or just this expression, okay. So if z is the principal axis, of inertia at C, okay, then I x z I y z will all be 0. In that case MB would be equal to I z z C omega dot plus RCP MACI. This is 3.32. Okay, all the xz and yz's would be 0. and you would just be left out with this term and this term. Similarly, if you have this MA written, okay, in this also, if axis 3 is the principal axis of inertia, then I13 and I23 would be equal to 0. So a lot of these terms would be 0 in that case. So I'm not separately writing, but always remember A is a point on the rigid body, and A can either be the center of mass or acceleration is 0 and so on. Okay, so we now discuss another special case, which is the Euler's equations for three-dimensional motion of a rigid body. Okay, so we want to first use the principal axis at A, just so that the expressions become simpler. And our point A is exactly as it was before, so let's put that down in word. The expression of HA is simple in terms of principal axis, just because all those I1, 2, 2, 3, 3, 1, all those terms will be all 0. Principal axis at A, and A is the point of the rigid body such that A is the same as center of mass, or the acceleration of A in the inertial frame is 0, or AI is along AC. So you want to now write it in terms of the principal axis. Okay, so EI is fixed to body at A. So HA can be written as, in the principal system, 0, 0. So this would be 0. Okay, so just write this out as a vector. HA is equal to I11 A omega 1 E1 hat plus I22 A omega 2 E2 hat omega 3 E3 hat. Now if you want to write MA, that would be H dot A terms of I, sorry, so EI is fixed in this I frame. Okay. That means sorry, you would then write it as plus omega cross HA. Okay, so for a rotating frame, you write it like this. Any vector is written like this. So HAI is no different. Okay, now you want to take a time derivative of this with E1 fixed, E1, E2, E3 fixed. Okay, so this would become so if E1, E2, E3 are fixed, then I11, I22, I33 will all be constant with time. We have used this point yet again. Plus this cross product can be written as E1, E2, E3. Now we want to take the sum of these terms common. So let's put it this way. E1 will club the terms together, so it would be minus I22A minus I33A omega 2 omega 3 E1 plus there will be similar terms of E2 plus E3. Okay, I'm not writing them, but they are quite clear what it should be. So the first component of the moment MA1 can be written as I11A omega 1 dot minus I22 of A minus I33 of A omega 2 omega 3. This is I22 of A omega 2 dot I33 of A minus I11 of A omega 3 omega 1. Similarly, the third component of the vector MA is I33 of A omega 3 dot minus I11A minus I22A omega 1 omega 2. Okay, so this is equations 3.34. Okay, so these are the Euler's equations of motion of a rigid body for a principal axis of inertia at A. So let me just write down. That was essentially the purpose of this particular topic, Euler's equations for three-dimensional motion. Euler's equation of motions, equations of motion of a rigid body for principal axis of inertia at A. Okay, now we can, just like the previous case, have some remarks mentioning some of the special cases. So you can see that these equations 3.34 are actually ordinary differential equations, because omega 1 dot omega 2 they are just differentials of time. They are also coupled because each one of them has this mixed collection of omega 1, omega 2, omega 3. Okay, so it's not independent, and it's clearly non-linear since you have square terms in omega 1, omega 2, omega 3. So 3.34 is coupled non-linear ODE in omega 1, omega 2 and omega 3. So if omega has somewhat of a fixed direction, then it's easy, otherwise it's slightly harder to go about. So what you want to do is you want to write this to get the orientation of this. You have to express omega in terms of the Euler angles, and let me do that over here. So their solution meaning 3.34 solutions. Does not directly give the orientation of the body in I frame unless omega has a fixed direction. So let's see how we can do that. Let's say this is E1, E2, E3. Okay, and so let's write omega is equal to theta dot. I'll show what the angle theta is. Let me just write that first. So use a different color, E1, E2, sorry, 2 and E3. Okay, now let me take another one, E3, E1 dash. So E1 dash. Okay, this is also E1 double dash. Let me draw all these angles first, and then I'll explain what these are. Similarly, E2 dash and E3 dash. Okay, now E1 double dash is, sorry, E1 double dash is this, E2 double dash is this, and E3 double dash. Okay, fine. Now let me point out to the angles. Let's have theta, phi, and psi. Theta, sorry, phi, psi, theta. Okay, so n is normal to E3 and E3 along E3 cross E3, along E3 cross E3. Phi is the angle between N and E1. Okay, so N1 is perpendicular to E3 and E3 along E3 cross E3. So you have seen E3 and E3. So N is perpendicular to E3 cross E3. So hence it's perpendicular to both big E3 and small E3. Now phi is the angle between N and E1. Okay, so that is already shown to you over here. It's the angle between N and E1 is rotation about E3. Rotation about E3. Okay, theta is the angle between E3 and E3, rotation about N. So this is called phi dot. Okay, rotation about N would be called theta dot. Okay, so phi dot and theta dot. Fine. Similarly, psi is the angle between N and E1, rotation about E3. So this is E3. This one is psi dot. Okay. Now the omega can be written in terms of these Euler angles, which are theta, phi, and psi, are phi dot into E3. Okay, plus this is psi. I should be more clear about it. Okay, then you would have a theta dot in the direction of N. Okay, plus psi dot in the direction of E3. Okay, now phi dot, how would one write E3? So E3 now has to be written in terms of E1, E2 and E3, small E1, E2 and E3. So let me just repeat that this black E3, okay, big E3 has to be written in terms of the green E1, E2 and E3. Okay, that's the objective. So let's first write the easiest component of it. That would be cos theta. So this would be cos theta along E3. Okay, then one has, you want to write it along E3. So first take a cos of phi or first take a sine of this, okay, that would be along this particular direction, and then take a cos of psi. So you would write it as sine theta cos phi E2 plus sine psi E1. Okay, so you have to do two projections like this, okay, plus theta dot theta dot would be, now you have to like project this n in terms of E1, E2 and E3. So clearly, I mean, since n is perpendicular to E3, it will not have a component along E3, so it will only be E1 and E2. So that would be cos psi E1 minus sine psi E2, and the last one is what, E3, so E3 is already there, that would be psi dot E3 hat. Okay, so once this is done, you can write sort of omega, so you club all the E1 terms separately, club all the E2 terms separately, and E3 terms separately. Okay, so you would get omega 1 is equal to theta dot cos psi plus phi dot sine theta sine psi, and then omega 2 would be minus theta theta dot sine psi plus phi dot sine theta cos phi phi dot plus phi dot cos theta. Okay, okay, now if you take say omega 1 dot after this, so you have to apply the chain rule, and you can write this expression, you can apply the chain rule, and you can write this expression, you can apply the chain rule, and you can write this expression. Now the reason we were discussing all this is because you will require omega 1 dot, omega 2 dot on omega 3 dot over here, other than requiring omega 1, omega 2 and omega 3. So that's how, I mean, these Euler's angles are useful in trying to solve these equations 3.34. So if you represent them in terms of this phi, theta and psi, then you should be able to solve them more easily. So this is one method to go about it. Okay, now similar to the case which we have previously discussed, if you have, for example, this MA, okay, if omega and omega dot are in the direction of the principal axis of inertia, which is E3, then this will just reduce to the E3 component. Okay, you will only have this E3 component if omega and omega dot are in the direction of principal axis of inertia. So this has been done before, okay, just over here as well. and say if this MA3, if this term is equal to 0, okay, then this would imply that omega 3 is a constant if this is 0, okay. So if MA3 is equal to 0, that would mean that this is equal to this, and omega 3 will be a constant if this particular thing will be 0. So I11 about A is the same as I22 about A. Okay. Now if this entire thing is 0, the entire moment about A is 0, then that would mean that the rate change of moment of momentum is also 0 in the I frame. That would mean that this moment of momentum is constant. Okay. Now this will not necessarily mean that omega will be a constant. So this being a constant does not imply that this is also constant. This is something which will be discussed perhaps later, slightly later on, if at all. Okay. So I'll put that down in words perhaps. Okay, since this is if MA T is equal to 0, then HA dot I of T is equal to 0, that is HA is equal to constant. Now this does not necessarily imply that omega is constant. Okay, this is something you can verify, see if you can. Okay. Again, I mean, if you have a arbitrary point, the moment equation for that would be, say, if you have an arbitrary point B, then you can write MB is equal to MC plus RCB cross F. This can be written as HCI dot plus RCB cross F can be written as MAC of I. So then you can write this H dot C, okay, as so let me just first write this term. So this would be RCB cross MAC I plus IXX of C omega x dot. So you should be looking over here, okay, trying to write HC, okay, because C is as good as a point as A, and this can be written as this term. So the 1 is x, 2 is y, and C is z, 3 is z. So this is IXXC omega x dot minus IYY of C minus IZZ of C omega y omega z I hat. Okay, and then there will be other terms. So this is, I'm just writing plus sign because there are a lot of terms, so I'm not writing all of them. This is equation 3.35. The point is that you can write this for an arbitrary point B, and obviously you would want to choose a point B such that you have lots of unknowns over there. Okay, let's now try to write direct equations of moment of momentum if I11A is equal to I22A. Okay, let's see what we can do with this. It's another special case. This is the third special case perhaps which we have been discussing. So let me first write in words, then I'll put it in figure, okay, and then we'll see the maths part of it. It's quite boring all the time to write what A is, but let's do that just for the sake of completion. Let A be a material point of a rigid body with EI as the principal axis at A. I11 of A is equal to I22 FA, and A is equal to C, or acceleration of A is 0 or is along AC. Okay. So this is something which we have discussed when we were discussing this principal axis. Every axis n which is perpendicular to E3 is a principal axis as A, with INNA is equal to I11A for all n. Okay, check this. We have shown and proven this. Please check this part. So let me draw the relevant diagram. So okay, so this is the point A. I'm drawing a frame like this. This is 3, 2, 1, 5 dot. Okay. So let me first draw an N. I'll draw it with another ink. This one. So this n is clearly perpendicular to E3. So I would show it like this. Okay. And then let me draw the rest of it. It is body which is rotating by omega. This is a frame M rotating by capital omega. Okay, and this is a fixed line in body. This forms an angle of phi with E2. Okay, and this n forms an angle of theta with E1. So that's about it from the figure. So let's see. Every axis n perpendicular to E3 is a principal axis at A with I and n is equal to I11 for n. Hence the axis EI are chosen so that axis E3 is aligned with the principal axis 3 at A. Well, this is something which we have already somewhat done in the just two special cases which we have studied. The axis EI is chosen so that axis E3 is aligned with principal axis 3. Axis 3 at A. Okay, and is fixed to the body. The axis E1, E2 could rotate relative to with respect to rigid body about E3. I think the figure itself shows about the rotation of this. So, and the rate at which it does is that phi dot E3. Okay, that is already shown in the figure. This would automatically imply that I11 of A, I22 of A, I33 of A remains constant for all positions of E1, E2. Okay. So I hope you can understand how these rotations are happening. E1 and E2 can rotate with the speed phi dot about E3. Okay. Now let M be the frame which is attached at A with EI fixed to it. So M is a frame with this is attached at A with EI fixed to it. Okay, so E1, E2, E3 are rotating. I mean E3 is not rotating, but E1, E2 are rotating about E3 in the body, but they are attached to the frame. So with respect to the frame, they would not be moving. Okay. The angular velocity omega, big omega of the frame M differs from the angular velocity omega of the rigid body in its E3 component. So let me write out first. The big omega of the frame M is written as omega 1 E1 hat plus omega 2 E2 hat plus omega 3 E3 hat. Okay. this would be written as omega plus phi dot E3. Okay. I mean, the answer for this is quite simple. I mean, you have to see the angular, relative angular rotation. Okay. So the rotation of the frame M with respect to the body, that is what you have to see. Now you can write omega is also a vector, and it can be written as omega 1 plus omega 2 plus omega 3. So this would imply that omega 1 is equal to, sorry, omega 1 is equal to omega 1, omega 2 is equal to omega 2, omega 3 is equal to omega 3 plus phi dot is not equal to omega 3. Okay. Now we want to just use the moment of momentum equation, the relation between moment of momentum and the angular rotation, essentially the Euler's equation. So HA is equal to I11A omega 1 E1 hat plus omega I22A omega 2 E2 hat plus I33A omega 3 E3 hat. Clearly we are in the principal axis, principal system. So you have I11 of A omega 1 E1 hat plus omega 2 E2 hat plus I33 of A of 3 omega 3 hat. Okay, because I11 is equal to I22. Okay. 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 Fine. Now we want to apply the Euler's axiom. So that would mean that this, okay, I always comes up automatically since the Euler's axiom has been used. Now this will again have EI as constant plus omega, big omega HA. So I11A omega dot E1 hat plus omega 2 dot E2 hat plus I33A omega 3 E3 hat. Okay, plus omega cross HA. Is 3.36. So you can use this if you have, say, a body of revolution like the one which we have considered over here. Sorry. Okay. So this is a much more useful form than the ones which we have seen before. So we should try to use this more often. Okay. Since a lot has been written about the moment inertia and how the moment of momentum is related to the omega So you can see that how we are writing everything in terms of I, okay, the inertia matrix for this study of dynamics. We can now also discuss what would be the kinetic energy representation. We are writing of a rigid body all the time, sometimes missing, but it's quite obvious that this course is entirely about rigid bodies. So maybe if I miss a couple of times, it's not a problem. Okay, so we have earlier seen that the kinetic energy, say, of you have this body. Now I'll just draw it. It's the same body again and again, okay? So please don't pull me up for not drawing the exact diagram. So if this is a small mass dm, this is the point P, okay, and this is a total mass m. This has an angular speed of angular velocity of omega. Okay. C is the center of mass, and this vector is rpc. Now we have shown before that T is equal to half into mvc square plus half into mvpc square dm. Okay, so this was long back, I think, when we were discussing force axioms and force systems. Let me just try to pull up the equation. Yes, so we had written this in equation 2.31. Please go and check the derivation if you do not exactly know how this has been written. Okay, you can pause the video and go back and check this. Okay, so once this is done, I'll write it as half mvc square plus half into m vpc. How do we want to write it? We can write it as omega cross rpc dot vpc to tm. Okay, so this term is vpc vector. Okay, now we can write it as half fvc square plus half m r pc cross vpc dm dot omega. Okay, half mvc square plus half m, this is actually the moment of momentum, so this will be hc dot omega. Okay, this entire thing will be, this integration will be hc. One question which we have over here is this: how is this written as this? Okay, so please try to come up with a reason. How can this be true? I think you should be able to do this. Okay, now we want to sort of take this dot product over here. we'll write this as T is equal, so let me write it separately. Hc dot omega is, as you know, Hci omega I in the index notation. So it will be Hc1 omega 1 plus Hc2 omega 2 plus Hc3 omega 3. Okay. Now this Hci can be written as Iij C omega I omega j. Okay. For this you will have to check which equation. Yes, please check equation 3.2. Check, when I say check, don't just look at the equation and confirm that that is okay. Please also see how it had been derived, so how we had come to this. Okay, fine. So I mean, omega I and omega j can be interchanged. There's no, it's a just you can change the position of it without affecting what it really means. And to see what it really means, you have to just expand it. So it will be 3 terms each, so total 9 terms. Okay, so once this is done, we can write it as half mvc square plus half hc dot omega. Now hc dot omega, we want to write it as half iijc omega I omega j. This is 3.37. Now this clearly you want to expand. Okay, so as I've said, once you expand it, you will get 9 terms, but I want to only write this in the principal coordinate system. So automatically all the 1 2 2 1 3 2 3 1 and so on terms will disappear. So in the principal system, I will be able to write it in this form. So you have half into I11 of C omega 1 square plus 2 2C whole star omega 2 star whole square plus I33 of C star omega 3 star whole square. Okay, so the star automatically refers to the principal axis of inertia at C. So this would have been 3.38 if you had expanded it into the general terms, and then 3.39. So this is the whole point. The kinetic energy will not really change. I mean, just because you rotate the coordinate axis, the total kinetic energy will not be changed. Obviously the numbers change. So I11 of C star is not clearly equal to I11 of C. Okay, so the numbers will keep on changing, and we have discussed this several times. Okay, so star refers to the principal axis of inertia at C. Star refers axis of inertia at C. Okay, and one term is clearly the translating term and the other is the rotational kinetic energy. So TR is half mvc square translational kinetic energy. Okay, and the other TC and TR is equal to half into this hc dot omega is equal to half iij c omega I omega j. This is also equal to half p dot vc. Rotational kinetic energy. Okay, so this would mean the body was translating at vc. This would mean as if the body was rotating about the center of mass. So these are two separate components. Please don't think of them as some sort of a principle of superposition or anything like that. Okay, these are two separate terms, that's all. Okay. Now if you have say if a point A of a rigid body, say I should delete this from over here because we are not really discussing it. If a point A of rigid body has VA equal to 0, then VP is equal to VPA is equal to omega cross RPA. Let's see that in a figure. So if you have something like this, A, P, you have the small mass dm, RPA, the whole mass is m, rotating by omega, and VA is equal to 0. Then VP is equal to omega cross RPA. In this case, T will be equal to half into m VP square dm. Okay, the reason is that we can write this as omega dot RPA dot VPA. Okay, so this would give us a VP square, and again by the same logic which you should have figured out, which I had mentioned in red, I can write this as RPA cross VPA dm dot omega. This is equal to half into HA dot omega, and this is equal to half into IIJA omega I omega j. This is 3.41. Okay. Okay, so this I want to write in the expanded form again, 9 terms. Okay, some of them will be symmetric, so not writing, but in the principal one I'm happy to write. So I11 A star omega 1 star square plus I22 A star omega 2 star whole square plus I33 A star omega 3 star square. This is 3.43. Again, this refers to the principal axis. Okay. So, I mean, the way this kinetic energy has been calculated over here is just that you take up a small mass of it, and what would be the kinetic energy of that mass, and then integrate this over the whole volume. So that has been done over here. Okay. Now if you have an instantaneous axis of rotation, you do not recall it, please go back and check. So if you have, say, something like this, have this as dm, so the point P, we have r, this is the point A, this is omega. Okay, so this is the instantaneous axis of rotation. So if you have the instantaneous axis of rotation of the rigid body that will exist through this point A, then T can be written as half again mvp square tm. Okay, and then this would be half m omega r is shown over here, omega is also shown because this is instantaneously rotating about this axis. Okay, so omega r whole square dm, and this would be half into r square dm omega square, half omega just to indicate it's along this axis. Okay, we could have written as omega nn or whatever, but since this angle axis is omega, we can just write it like that. Okay, so this is 3.44. So I omega a is the moment of inertia about the instantaneous axis of rotation. Is the inertia about the instantaneous axis of rotation. So for the case, if you have, say, omega is equal to omega E3, okay, then you can combine this 3.37, this one, okay, and 3.44, okay, so that would give us, say, T is equal to half m vc square plus half I33 c omega square. 3.45. So VA would be equal to 0 clearly. That's why we are able to get it. So you have to use equation 3.37 and 3.44. And this did not require E3 to be the principal axis. Okay, nowhere. So this is something which you should verify. Verify the validity when E3 is not a principal axis. C, okay, or A. So you should please verify it. What do I mean by verify? Please pause the video, go and check the definition of how we have arrived at it, and make sure that there was no use of E3 being the principal axis. So E3 is just that, in this omega is along E3, that's all. Okay.